When we look up at the constellation Leo, we're not just seeing an ancient symbol of power. What we're actually doing is peering through a window into a region of space, a region just teeming with some of the most fascinating and frankly extreme physical phenomena in our galactic neighborhood and far, far beyond. So let's begin our scientific investigation.
All right, here's our roadmap for this exploration. First, we'll pinpoint Leo's location on the celestial sphere. Then, we'll dive into the physics of its principal stars. After that, we'll examine a couple of profound astrophysical extremes, journey into the deep universe to see galactic structures, and we'll wrap up by looking at its deep cultural legacy.
Okay, so first things first. Before we can analyze anything within Leo, we need to define the parameters of our subject. We have to establish its precise location, its scale, and its observational coordinates from our vantage point right here on Earth.
And Leo is a significant constellation. I mean, it covers 947 square degrees of the sky. To put that into perspective, that makes it the 12th largest of the 88 modern constellations. That's a substantial piece of celestial real estate. Now, its position on the celestial sphere gives it a huge zone of visibility. Observers from latitude plus 90 degrees, that's the North Pole, all the way down to negative 65 degrees can see the constellation in its entirety. This means it's accessible to almost the entire population of our planet. As this timeline shows, there's a distinct annual rhythm to Leo's appearance. For observers in the northern hemisphere, the prime viewing window is during March and April. Now, as you can see, between August 10th and September 16th, the sun's passage through its astronomical boundaries makes it invisible, lost in the glare of daylight.
All right, let's move from its overall shape to its constituent parts. The recognizable form of Leo is really dominated by an asterism known as the sickle, and it contains some truly remarkable stars. We're now going to analyze the physics of its three most luminous members.
At the heart of Leo, we find Regulus. As this direct comparison with our own sun clearly demonstrates, its physical parameters are, well, extreme. Notice its mass is 3.5 times that of our sun, and its luminosity is a staggering 160 times greater. But the most striking parameter here is its rotation period, a mere 15.9 hours. That's in stark contrast to our sun's leisurely 25-day rotation.
And this extreme rotational velocity has a profound physical consequence. The centrifugal force generated at its equator is so immense that it partially counteracts the star's own gravity, causing it to bulge outwards. This phenomenon sculpts its true shape. It's not a perfect sphere, but an oblate spheroid, significantly flattened at the poles. Think of a spinning water balloon.
Now, let's turn our attention to Algieba. Through a telescope, it resolves into a spectacular binary star system. These two giant stars are gravitationally bound in a slow dance, taking over 500 years to complete a single orbit. What's more, in 2009, the presence of a massive exoplanet was confirmed, a gas giant with 8.8 times the mass of Jupiter orbiting one of the component stars.
Finally, we come to Nebula, the tail of the lion. This star is a key laboratory for studying planetary evolution. Why? Because it's surrounded by a substantial disk of cool dust, very similar to the one observed around the star Vega. This is a strong indicator that the processes of planet formation could very well be underway there as we speak.
Beyond its bright primary stars, Leo is also home to objects that push our understanding of stellar physics right to the very edge. We're now going to investigate two such extremes, each serving as a natural laboratory for astrophysical research. Lurking in the direction of Leo is one of our sun's nearest stellar neighbors, Wolf 359, a tiny red dwarf just 7.8 light-years away. To really grasp its faintness, let's run a thought experiment. If we were to replace our sun with Wolf 359, high noon on Earth would be only 10 times brighter than a night with a full moon. This bar chart here visually quantifies that staggering difference in illumination. Now, we shift to a far more violent system, DP Leonis, a cataclysmic variable binary. Let's break down this process step by step, as shown here. First, a white dwarf and a red dwarf are locked in an extremely tight 90-minute orbit. Second, the white dwarf's intense gravity rips plasma from its companion in a process we call mass transfer. Third, an intense magnetic field captures this stream of plasma, funneling it along the field lines. Finally, this plasma slams into the white dwarf's magnetic poles, releasing a tremendous amount of energy.
Okay, now let's broaden our view beyond the individual stars within our own galaxy.
Gazing through Leo allows us to peer into the vast structures of deep space, revealing the large-scale architecture of the universe itself.
The most famous deep sky object in this region is the Leo triplet, a small group of galaxies. And the number on this slide gives us a sense of scale. They are 35 million light-years away. The light we're seeing from them began its journey when mammals were just beginning to dominate the Earth. This triplet includes two spiral galaxies, M65 and M66, and this one, NGC 3628. We happen to see this galaxy perfectly edge-on, which has earned it the nickname the Hamburger Galaxy. That dark band you see is a thick lane of interstellar dust, obscuring the light from the galactic core behind it. But even this galactic group is dwarfed by the structure that lies beyond it. In the same direction, at a much greater cosmological distance, we find one of the largest known structures in the observable universe, the Sloan Great Wall, a colossal supercluster of galaxies, a filamentary structure stretching for more than 1 billion light-years.
Having journeyed to the cosmic horizon, we now return to the human scale. For millennia, long before we understood its physics, this pattern of stars held deep cultural and mythological significance for civilizations across the globe. The Babylonians, for instance, identified it as Mul.Ur.Gu.La, the great lion, a guardian of the celestial gates. For the ancient Egyptians, its heliacal rising, that's its first appearance in the dawn sky, coincided with the scorching summer heat and the life-giving annual flood of the Nile River. But the most enduring myth comes to us from the ancient Greeks, who associated the constellation with the first labor of Heracles. The challenge was the Nemean lion, a monstrous beast whose hide was enchanted, making it impenetrable to any known weapon. After his arrows and sword proved useless, Heracles realized conventional weapons were futile. He resorted to brute force, cornering the beast in its lair, stunning it with a club fashioned from an olive tree, and finally overpowering it with sheer strength. Now, the apotheosis of this story lies in its final, clever detail. To skin the impenetrable hide, Heracles deduced that the only tool sharp enough to pierce it would have to be one of the lion's own claws. To commemorate this victory of both brawn and brains, Zeus placed the lion among the stars.
And you can find this legendary figure in your own night sky by following these simple steps. First, locate the Big Dipper. Second, draw a line through the two pointer stars at the front of its bowl, Merak and Dubhe. That line will point you straight to Leo, where you can identify the sickle asterism that forms the lion's head and mane.
So, the key takeaway is this. The constellation Leo serves as a manifestation of nature's grandeur across every conceivable physical scale. From the stellar dynamics of a rapidly spinning star just a few light-years away, to the silent, majestic spirals of galaxies whose light has traveled for millions of years. It's a constant reminder of the profound complexity of the cosmos, leaving us with the ultimate scientific question. What else can this window into the universe teach us?